Disentangling color and shape representations for continual learning. This is a paper for the Continual Learning workshop of ICML. This is a project led by the CBC in Barcelona and funded by the Huawei Kirin solution. To give you a hint of what is feature disentanglement about, let's put a simple case. We have two sets of objects, say blue squares and red circles, and we would like a model that is able to recognize either of the two with different combination of features, say red squares and blue circles. With traditional CNNs, the feature extractor is entangling color and shape representations. Both representations are shared throughout the network. However, if we manage to disentangle these two features, color and shape, then such architecture would be able to recognize indistinctly between these two features. Sharing distinct feature representations can lead to catastrophic forgetting, as we are adapting the network to incremental tasks, as we integrate different features in only one network or layer. Instead, with the disentangled space, we are able to distinguish these two features in the same representation. It was mentioned in previous studies that disentangled representations can better generalize for several tasks, and this can lead to an overall lower forgetting. Continual learning tasks can be presented as task-aware, where we have one head per task in a network, or task-agnostic, where one head is incrementally growing for every time we add a task. We propose in this work a network that processes color and shape separately to prevent this interference, also retaining capacity. We want to design a network that is able to perform disentanglement before the binding effect of a spatial relationship between color and shape. Let's put the example of ResNet 18. In the ResNet 18, we have an initial convolutional layer with a pooling layer, and then we have 4 blocks of convolutions, which are added as residual layers. Then we have an average pooling, where the spatial relationships are erased and integrated to a linear layer, which will be our head for this classification task. For the case of disentangling color and shape, what we do is, for the first case, in color, we change the convolutional kernels to be one by one, so that we have no spatial relationships between the network. For the shape case, what we do is to change the preprocessing step of the image, namely that we change the image to have a grayscale image, so that we don't have color information. In order to design a network that is able to integrate these two types of features, color and shape, let's assume a scenario. We have two tasks, which we have two classes. And the way to integrate these two classes when learning, we have two different designs. One design, the undesired, namely that we have an entangled space, is that we have the feature extractor that learns shape and color, but on every head we integrate these features indistinctively. The network is unable to generalize for both representations to one unique representation on every head, so that for every time we need to learn the task 2, these two representations are entangled on every head of the new task. For the desired case, we can learn every single representation on the head, while in every task we learn different features, as is this case of blue square and a yellow square. So that here we have disentanglement in the feature level and disentanglement in the task level. For this, we designed a network in which has 3 parts. In the first part, we have the different feature extractors, which would process in this case color and shape separately. And then we have the merging part, in which we merge these two representations. And we do this in the dimension where the spatial relationships are kept. And the last part, we have the integration part, the head for every task. For the specific case of the ResNet 18, what we have done is to consider a different head. In this case, we modified the head, adding a convolutional layer, an average pooling inside the head, and the usual linear layer for classification. The reason why we do this is because once we have concatenated color and shape, what we need is to keep the special relationships between these two layers so that we can integrate on the average pooling for every individual task. And now I'm going to show results for this ResNet case. To test our network, what we have done is to split a dataset, for this case the Oxford 102 flowers dataset, in 10 tasks. And also we tried the state-of-the-art, which would be the ResNet 18, with different continual learning approaches. Also, we have added a modified version of the ResNet 18, which has the head that we defined previously. What we can see is for the task aware that we acquire much higher performance on the fine-tune, about 12% on increase of accuracy, and we get highest using the learning without forgetting. With other approaches such as elastic weight consolidation, memory-aware synapses, and synaptic intelligence, we still keep a higher performance with our disentangled measure. Also, we have to pinpoint that for some cases of color or shape, we can acquire higher performance than the ResNet 18. Also, that the modified head over the ResNet 18 does not improve from the original ResNet. For the task agnostic case, similarly, we get higher performance on the fine-tune case, and also we get highest performance using one of the approaches, for this case the elastic weight consolidation. For the case of forgetting, we have analyzed the drop of accuracy between the tasks. In the case of task aware, we get lower forgetting in the fine-tune case, and we get the lowest forgetting on the memory aware synapses. Also, we can see that for the shape case and the color case, we get lowest forgetting in comparison to the state-of-the-art. For the task agnostic case, we get much lower forgetting on the fine-tune case, about 20%, and we get the lowest forgetting for the memory-aware synapses. Another thing is that we have tested is the overall accuracy after training the last tasks, so that we can see the accuracy of every single task after training the last task. We can see here with different colors the different networks that we have tried, and we can see that the disentanglement network in red gets much higher accuracy for every single task, for most tasks. We have to pinpoint again that the color or shape branches alone sometimes outperform the state-of-the-art in some of the tasks. Similarly, we analyzed the drop of accuracy, namely the forgetting, after training the last task. And we can see that our disentanglement network gets lower forgetting in comparison to the ResNet 18, and also every network of color and shape gets lower forgetting overall than the original ResNet. This happens for both task-aware and task-agnostic settings, where we can see that the forgetting in the task-agnostic setting is much higher. We have one head which we have to train in every task we add. We have also analyzed the accuracy for every task sequence, namely that we have evaluated every task on every task that we have added. And we can see that for the fine-tune case, our network represented in the red line gets much higher accuracy in comparison to the ResNet 18. And also the slope of accuracy is much more flat than the case of the ResNet 18, which is much more steep, as well as the other networks. We have tested this in comparison to different regularization approaches, and we can see that for most cases, our network represented in red gets much higher accuracy in comparison to the original ResNet. And this happens for the learning without forgetting, elastic weight consolidation, synaptic intelligence, and memory-aware synapses. In the future, we will propose different implementations with different networks, such as AlexNet or PGG. We think this work has shown very promising results only with one dataset. We think that for some datasets, color would have more importance or shape would have more importance. That's why we would like to try it by running different datasets, such as the DTD with textures or TinyImageNet with real objects and semantic attributes. Also, we would like to try to run experiments with examples or rehearsal. Also, dissect the network, printing the filters of the shape branch, and also the RGB distribution from the color branch, so that we can get better assess which features are forgotten and how these features are forgotten throughout every task. We also think to add an ablation design, testing the effect of binding when we change the average pooling before the merging. Also, doing the binding but removing the disentanglement so that we don't have a linear layer on every task head. We're also thinking of alternatives for the color branch, such as smoothing the image and adding it as a channel in the color feature extractor. Also, other strategies such as color naming or descriptors. This is the end of the paper. Thank you for listening, and you can ask anytime through our email or through the Zoom link of the ICML. Thank you.